Swayam Prabha. Digital India. Educated India.
All right, let's get started. Okay, so we are done with 2 quantum. Let's do another example. Okay, let's take a condition where I don't have coupled oscillators. So I don't have coupled oscillators, but you are in the so-called weak coupling regime where I can still have some kind of interaction between 2 molecules. It's not coherent coupling, but I could have some kind of population transfer, energy transfer between one state to the other. How would this manifest in a 2D line shape? Right? Let's again talk about this particular scenario where I have omega A, omega B, 2 oscillators, right? And let's say I'm looking at my rephasing signal, and everybody is comfortable now, I suppose, about that excitation pathway that I have just included. What would this be? Where would this feature appear on the 2D map? This excitation pathway? Not you. Sorry, I didn't mean to stop you there. Let's see if anybody else gets. Where would this feature appear? Off diagonal? Off diagonal? Off diagonal or diagonal? There are only 2 places. How would you know? Exactly. So your first excitation, this is rephasing, it's not 2 quantum, is 0B. So you're going to be absorbing. Excitation is at the energy of this. And then the emission is also coming from that. So it will be on the diagonal. This is the ground state bleach. Right? But off diagonal, would I ever have an off diagonal for this particular case of weak coupling? Would I ever have a scenario? Without energy transfer, would I have a cross coupling, a cross off diagonal thing? There's no way, right? If I don't have this arrow, for example, I will not have cross coupling because I cannot excite using the same coherent pathway the 2 molecules. One molecule is here, one molecule is there. If I excite this molecule, I cannot come back and excite this molecule. It's completely different excitation pathway because it's not excited. Coherence is not generated. So if I don't have coupling, I will never be able to generate off diagonal term. Even if you don't understand, keep this in mind, go back and think about it. It's very kind of critical. Now let's say now we let the population evolve. This is, let's say, it's time 0 population time, which is 0 delay between this pulse and this pulse. I come with this pulse, immediately I generate the final interaction and I measure, let's say I evolve in some time. So I'm changing the delay between my second and third pulse, so what we call as population waiting time, right? So I create this population, I wait for some time, and then come with the third pulse to generate the coherence. Now, while I wait, it could happen, like pointed out earlier, title of the slide, my population can wander around, find the other molecule, and transfer itself. Right? Agreed? So if I do something like that, then there is some population evolution. Now the population has moved from my B state to my A state. Again, I made a mistake here. It should be A. Sorry, there's a mistake here. So you create an A state. Let me fix that. Okay, so now I evolve. Now the population has reached A state. Okay, and then now I come with the third pulse. I generate a coherence at 0A. So earlier, there is no way I can go through the B state and generate a coherence on the A state unless there is energy transfer. and this will appear off diagonal, but this off diagonal coupling will not be symmetric because I cannot do the same thing going from the A side. Imagine writing the same Feynman diagram for the A. Let's say this is A population. How much ever time evolve, I cannot go up the ladder. I cannot transfer back up the energy, right? I cannot, in some cases I can, but let's say in general case, I cannot. Then I will not be able to see going through my A coherence emission from the B coherence. It will never happen. So in the presence of energy transfer, I will have a very strong asymmetry in my line shape with one of the off diagonal elements much stronger. Okay. Now take the case where maybe I already start with some coupling. If I already have some coupling, so let me just point that out. So what you will see now is at time 0, you will see only 2 bleachers. There is no off diagonal features. Now if I have energy transfer, I will see, and then what you will see is that there is a cross term which evolves. There will be no cross term on the other side. You will see a cross term. You will not see a cross term here. Okay. Now it so happens that I could start out with a coupled oscillator where at time 0 I have some symmetric features along off diagonal terms, have symmetric features, and in addition if I have energy transfer, then you will see the relative weight of one of them increasing. Okay, and that is signature of coherent energy transfer. Remember, it's a coherent transfer because my system is remembering it. I'm going through a coherent excitation pathway. It's a signature of energy transfer, and in fact, it can be used to measure energy transfer pathways. This is one example where you see the off diagonal feature gaining in intensity with population waiting time. From early time, you see barely something. Then as you wait longer, you start seeing a much more significant energy transfer. This again is in an FMO complex, a biological light harvesting system, where there is energy transfer happening in hundreds of femtosecond time scale, very fast transfer. Now that's again another utility of 2D spectroscopy. You can kind of pinpoint and measure energy transfer rates, which is at very fast time scales, and you know exactly where it's going, right? It's kind of powerful. The only thing that you need to deal with, again, remember, 2D is bloboscopy. You're dealing with blobs moving. Hopefully later on Wednesday, I will show you some data which is more convincing about energy transfer. We'll talk about it later. Okay, questions? Good point. Oh my God. That's a very, so what Adrija was pointing out is that here I'm starting out with nice oval-like line shape, and here it becomes circular, right? Now that's a very good question. Yeah. I'm sorry, let me take out my laser pointer. So here time 0, it's along the diagonal and becomes circular. Which is something I'm going to talk about in some time, but I'll not talk about it in detail. I thought of making a complete section on that, why this is happening. I didn't, which was my mistake. I apologize. Maybe I'll do it next time. So what happens is that we will show in some time that any kind of broadening along the diagonal, which we already kind of discussed, is because of inhomogeneous broadening. And along the antidiagonal is homogeneous broadening, right? Now, if I wait long enough, my homogeneous broadening is all done. It's kind of done already, right? So if my population evolves, it's going to scatter around, right? Kind of going around all possible inhomogeneities. So once I go towards inhomogeneity, I will distribute my population even along my antidiagonal. Even my antidiagonal becomes like inhomogeneous broadening, okay? So it's because at initial time, you have the homogeneous broadening and inhomogeneous broadening. Inhomogeneous broadening is because there is wide site-to-site disorder in the system. There is disorder in the system, and I'm spreading it only along the diagonal, okay? Because that's the only contributor to whatever the term, which I will show you in a while mathematically. But over a period of time, my population now has time scale to evolve and find other disorder points in the sample. So I'll become this symmetric. Okay, we kind of spoken about spectral diffusion in the one of the previous lectures, if you remember. Go back to the notes, it will be there. Spectral diffusion is basically my system evolving and exploring all the inhomogeneities in the sample. This kind of change in the line shape is signature of spectral diffusion, which again, there is another beautiful paper from Andrei Tokmakov talking about spectral diffusion. Again, it's one of the first, I mean, in 2004, 2005 PRL. Again, it's a beautiful example of how you can see your system evolving and exploring all possible inhomogeneities in time that you can kind of measure directly in the spectroscopy. Thanks for that question, Adrija. I hope I answered at least some part of it, but it's for that we need to understand the line shape a bit better, which we currently don't, or at least we don't yet. So because we've spoken about line shape, let's look at the line shape. Now, if I take the expression, so let's take a situation where I have only homogeneous damping. So the damping term, remember, there's a damping term in my polarization or the impulse response function, e power minus gamma t, right? Now, we have already seen how in the presence of inhomogeneous broadening, it will not be just e power minus gamma t, but you'll also have some delta square t square over 2 kind of form for inhomogeneous broadening for some broad Gaussian distribution. Let's forget that inhomogeneous distribution. If I just take damping of the coherence because of very fast fluctuations, I will just have e power minus gamma t. And in that case, I can take my expressions for my time domain impulse response functions, do a Fourier transform for a frequency representation. We have spoken about that, how we can do the frequency representation by taking a Fourier Laplace transform of my impulse response function, or Voigt transform to be precise. And you can derive analytical expressions of this kind. A beautiful looking Lorentzian form. You can plot this. This is pretty simple Python code. You can try this out if you want with the gamma parameter bit damping. And there is a real part of the refacing, non-refacing, imaginary part of refacing, non-refacing. As you can see, real part is symmetric along the diagonal. By the way, here I'm following the correct convention. My refacing will be negative in this, will be going this way. My non-refacing will be going this way. So don't get confused. Or if you get confused, don't blame me because of the community, not just me. Everybody plots in slightly different way. But in this case, this is a diagonal. This is anti-diagonal. It's symmetric, and you have imaginary part here, and this is absolute value. This is refacing, non-refacing. Sometimes you will also see in literature people just adding up refacing and non-refacing spectra. If you just add up refacing and non-refacing spectra, you refer to it as your absorptive or a total line shape. Think of it like your refacing spectrum is basically R2 and R3 of your correlation functions. Your non-refacing spectrum is R1 and R4. If you add all of them, what will you get? You'll get pump probe with just spectral resolution. So that is this. It's pump probe with some spectral resolution, but it's basically what is referred to as the total absorptive line shape. Basically, you're throwing away some important phase terms there, which is loss of information. Basically, if I write out all excitation pathways, you will see that if I add them up, the coherence terms kind of cancel each other because of phase difference. They destructively interfere. You will see only population dynamics in total absorptive. So if I take refacing and non-refacing and add them up, you will basically lose information of coherence. You will only get population dynamics like you will get in a pump probe measurement. Okay, so this is how it looks. It looks nice and clean, nice star shape. I call it star shape, but it's actually, if I take a cut along any axis, you will see it's a beautiful Lorentzian function. Okay, it's very nice. But the reality, before I showed you something, The reality is that you have inhomogeneous broadening with you. Okay. Now, even if you don't want to think about all the math that we derive, the way to remember inhomogeneous homogeneous broadening is that if I take any kind of spectrum, linear spectrum, it will have some line width which is Gaussian, and buried under this line width are the bunch, a distribution of Lorentzians. That's how you should think about it. Okay, your Lorentzians are coming from fast fluctuations, motional narrowing or homogeneous broadening. The broad distribution is because side to side disorder, slow fluctuation, side to side disorder. So one chromophore here, its energy is slightly different to a chromophore somewhere else. That distribution function is given by some Gaussian line width, right? Remember, when you're doing 2D, intrinsically, you're taking a two-dimensional correlation. You're taking a two-dimensional correlation. So if I have this wide distribution, a Gaussian distribution, let's say of states, I populate them, let's say, you know the ground state bridges of all of them will align themselves along the diagonal, right? So it's not inconceivable and kind of unreasonable to think if I take a cut along the diagonal, that will correspond to my inhomogeneous broadening, my side-to-side disorder, meaning that fundamentally each molecule, each chromophore that I have has slightly different energy. I excite it, I'll find it at the same point, but it will have a wide distribution. But my antidiagonal line width is representative of my homogeneous line width, because I know, looking at this guy, if I take antidiagonal cut along this, that will be a perfect Lorentzian, and that Lorentzian line width will be given by gamma. And inhomogeneous broadening will not lead to broadening in this direction, at least close to time zero, without population evolution, is something I alluded to already. Okay, fair enough. So, in principle, if I want to measure homogeneous and inhomogeneous broadening, I would say, very simple thing to do, take a 2D spectrum, take an antidiagonal cut, take a diagonal cut, fit the diagonal to a Gaussian, you'll get the inhomogeneous broadening, fit the antidiagonal cut to a Lorentzian, you'll get the homogeneous line width. Right? I wish it was as simple. It is not. That's because the contributions from them are kind of intertwined, and there will be contributions from one to the other. Now, I have a bit of notes. I will not probably go over this, but I will give these notes to you. There is a way to derive the line shape functions. When you take a 2D spectrum, take a cut along the diagonal or anti-diagonal, you can derive this. It's a bit of kind of exploration within the domain of 2D Fourier transforms. There are some very important theorems called projection theorems of 2D Fourier transform, which coincidentally were derived in the context of nuclear magnetic resonances. In fact, the original projective slice theorem of 2D Fourier transform appears in Journal of Magnetic Resonance from 1970s. It's kind of spectacular how completely independent field has developed tools that we can kind of invoke. Okay, so it's kind of a very nice methodology. I don't want to bother you with this. It's kind of mathematically a bit deep, but I have notes for it. There's also a beautiful paper from Stephen Condiff's group. If you're interested in that, Optics Express, I can give you those information. But this is all about those theorems. I'm not going to it. But now I can derive a particular two kind of coupled equations for antidiagonal and diagonal cuts of my refacing spectrum. Okay, which has, in this case, I apologize for this because I took it from my paper. In that paper, I call my capital gamma, small gamma, my delta to be delta omega, but you can kind of see this is your homogeneous line width and this is your inhomogeneous line width, and this is kind of there both along the diagonal and the diagonal. So it's kind of coupled. You cannot separate one from the other that easily. It comes with it and you have to live with it. But then you have these coupled equations. So what you do technically is that you take these two equations, which come saying the antidiagonal and diagonals are kind of present both, have both contributions of homogeneous and homogeneous broadening. You take a spectrum. There's a nice looking refacing 2D spectrum. By the way, for this, you should take the absolute value, not the real and imaginary. You take a diagonal cut and diagonal cut. It surprisingly looks Lorentzian and Gaussian, but it is tricking you because your eyes are not mathematically, they're not good at mathematical identification of mathematical functions. You have these lines that you show, the symbols here are actually, data, and the lines are the fits using these two equations. We fit both diagonal and antidiagonal cuts simultaneously. Okay. Then from the fit parameters, one can extract homogeneous and inhomogeneous line widths. Okay. If you haven't followed anything in the last 5 minutes, your takeaway message is this. Takeaway message is that if I measure a 2D refacing spectrum, in principle, my homogeneous line width will appear along the diagonal. Inhomogeneous line width will appear along the diagonal and homogeneous line width will appear anti-diagonal. The reality is that there is some kind of coupling, kind of contributions of both for both these spectra. So you have to use some kind of coupled equations which can be derived. I'm not going to bother you on this. I'll give you the notes for it if you're interested, because again, it's a kind of a deep dive into Fourier transforms, which I don't want to do in another direction. The takeaway is that we have to use these coupled equations to fit the line shape and extract very accurately homogeneous and inhomogeneous lines. Okay. And this is some example. We have kind of done it on different variants of my 2D perovskites here. We change the organic cation, we change the metal cation, so on and so forth. Always we get beautiful line shapes. We take cards and we can fit it and we get homogeneous and inhomogeneous line widths. Now you can ask me, why are we doing this, man? Why so much pain to measure homogeneous line width? Remember, homogeneous line width is associated to fast fluctuations, very rapid fluctuations, right? So we have kind of alluded to where the fast fluctuations comes. It's related to the nature of the bath. Nature of the bath, which is defined by the so-called spectral density. If it is super ohmic, where the spectral density scales super linearly with my frequency, then you're in the fast fluctuation limit, homogeneous line width limit. And it so happens the most critical baths in condensed phase, like phonons or many body interactions, are all super ohmic. Okay, they lead to rapid fluctuations where the correlations between the frequency fluctuations is almost close to zero. It's almost delta function. Okay, and it so happens that these many body interactions are critical for many other processes, including for recombination, for transport, and also maintaining coherence in the system in general. So it's kind of very important parameter, right? So if I want to characterize, if my aim is to characterize my system bath coupling with very high precision, I want to be able to measure these interaction parameters with high precision, then I need to be able to access the homogeneous line width, right? Right? I mean, one can say we can do photoluminescence. In fact, we do photoluminescence. Okay. What we do is temperature dependent photoluminescence. Basically, we measure this line width as a function of temperature. What am I doing by increasing the temperature? In this case, I'm interested in thermal defacing or defacing driven by a phonon bath. If I want to characterize that, what do I need to do? I need to measure my homogeneous line width as I increase my population in the thermal bath. How do I increase my population in my thermal bath? I just heat up the sample, right? So let's say I measure linear response, in this case, photoluminescence. I can measure the line width, okay? And the line width is scaling. It's increasing as I increase temperature. Makes sense. As I increase the bath, there's more scattering. more scattering, my line width will broaden. Okay. In fact, the full width half maximum, the line width, its dependence on temperature can be fitted beautifully with this equation. This is nothing but some exciton phonon scattering coefficient multiplied by some Bose occupation factor. Right? It's basically telling you what is the number density of thermal phonons in the bath. It's proportional to that. It kind of makes sense. Of course, here we are considering only scattering with longitudinal optical phonons and not acoustic modes. Acoustic modes scale linearly with temperature. Another discussion not for this particular course. Okay. So from here I can fit this data and I can extract this. Then you will say, come on man, it's done. What more you want? Two problems. One problem, the function that I use here, actually three problems. Let me start with first one. The first problem, the function that I use, you look at the line shape. Does it look like Lorentzian to you? It is not. It is not Lorentzian. Okay. It looks, we have actually used Gaussian. Gaussian is the most widely used function to fit photoluminescence line shape. Okay. But we have already seen linear response is more like a void profile. Okay. And we have also kind of seen how this fitting can be ambiguous. It can give me something which is kind of a mean on average of a homogeneous and inhomogeneous broadening, especially in a case where they are comparable. And then I won't be able to really say, okay, this is my thing. That's my first problem. Second problem, as I increase temperature, at low temperature, I see multiple peaks because in this case, there are multiple excitons. As I increase my temperature, I'm seeing a very broad peak. If I have multiple states already in there, they're kind of smeared out. So in fact, what I get as line width need not be representative of my actual exciton. It may be that wide distribution of states intrinsically present, and that's a problem. Second problem. Third problem, an important parameter that has to be extracted from this, is the energy of my longitudinal optical phonon. Okay. If I measure that, for this particular fit that I showed you, it's approximately 17 MeV. Now, for this particular system, we already know the optical phonon spectrum because we have done resonance Raman scattering, impulsive vibrational simulated Raman scattering. Remember all the vibrations that I showed, vibrational coherences that we are generating, and that's a spectrum. I hope you remember the spectrum from yesterday. And you see there is no phonon. I mean, I didn't show the data because it doesn't exist. Your phonons, also verified by theory, are all between 2 to 6 MeV range. So I'm not getting a right number. Of course, one might argue I may be oversimplifying the problem. I'm not using the right problem. True, but the first two problems still remain. That I'm not sure if I'm actually measuring homogeneous line width in this. So the way to overcome this is measure the homogeneous line width with highest possible precision, right? And we know how to do that. We do 2D spectroscopy. You just collect 2D spectra at different temperatures, right? And that's your homogeneous line width estimated at different temperatures. These are two different samples, doesn't matter. They're all increasing. Very nice. Now let's look at the parameters. Now you will say, oh my God, it's so much for nothing, man. It might happen like that, but let's see that. So there are two excitons, remember, there are two excitons. Here, thankfully, because of spectral resolution that I have, unlike photoluminescence, I can estimate the defacing of the two excitons separately, which is good. In the photoluminescence, it's a broad distribution. I don't know what I'm measuring. There's only one singular peak. Here it's distributed along the diagonal, so I can follow it very nicely. Now for exciton A, my energy of the phonon comes to be 6.5 MeV. Okay, and in the Raman spectrum, we do see a phonon at 6.5 MeV. So happy in both the systems, even in this system, it kind of see it. But exciton B, I get a phonon which is 21 MeV. There is no phonon at 21 MeV, right? And you can kind of see that the value that I get from photoluminescence is somewhere in between these two values, right? Kind of seem to be some kind of, not average per se, but some kind of value in between, 17 MeV. Now, to be really frank, I have to be honest, we still don't know why this is the case. We are able to measure this, and we are measuring a phonon energy, especially for one of the exciton B, to be 21 MeV. We don't know why it is the case, why is not the phonon appearing, but at least we know one thing. We know that we are truly measuring homogeneous line. Now we can go and explore what are the intricacies, what could be the problem now. With the photoluminescence, I would never know. I would still have this ambiguity intrinsically present in my system. Okay? Okay? Okay, so phonon is one kind of bath. Can you name any other kind of bath which could also be superomic? So I create an exciton, but I'm not creating only one exciton. I'm creating a bunch of excitons. Okay, and excitons can have collisions, right? They can come and hit each other. Let's say these collisions are elastic, so quasi-elastic, so kind of small fluctuations. They're not large, like formation of bi-excitons and stuff like that, but quasi-elastic, which means there are small fluctuations. And this can lead to defacing as well. This can lead to homogeneous line width as well, right? Agreed? Everybody is fine with me? Okay. Now, how do I measure this homogeneous line or broadening due to many body scattering or multi-body scattering? For temperature, we increase the temperature. We increase the thermal bath. What should we do for measuring many body scattering? Increase the excitation density. Okay. So, there is a specific term for this. It's called excitation-induced defacing. Excitation-induced defacing. It's basically the many body scattering, which is leading to defacing. And the way to do it is you simply increase the pump fluence. Okay. You increase the pump fluence. I mean, I'm extremely proud of this data that I'm showing here because we have done this measurement over 3 orders of magnitude of fluence, which is, I'm very pleased about it. As experimentalists, we're always happy to look at beautiful data. And what you see here, this is plotted in logarithmic scale on this side and linear scale here. This is a perfect straight line. It's a perfect straight line given by this equation here, where the slope of this is a direct measure of exciton-exciton scattering. It's a measure of how strong my many body scattering is. It's a measure of the many body interaction potential. Okay. And that's a very important critical parameter. This is done again in perovskites. And it so happens that the many body interaction parameter for this system is 2 to 3 orders of magnitude smaller than other 2-dimensional materials, including transition metal like alkylgelides. We'll not go into why and how. But then the point is we can extract the many body scattering using again 2D spectroscopy, measuring line widths. Now it's good, since we are, let me finish this first. So it so happens what I have shown you is just absolute value. There is many body scattering, I told you this, right? And this many body scattering, we are able to kind of model this by considering scattering of an exciton at k equal to 0 with exciton at non-k equal to 0, a bit of a detail. But another indication of many body scattering happens to also come not only in the line width of your absolute value of the refacing spectra, but also the phase of your signal. Okay. Like remember in the previous example, like in 2D IR and so on and so forth, you had absorptive line shape for the real part and dispersive line shape for the imaginary part. And here you'll see in the presence of many body scattering, this is dispersive and this is absorptive. Kind of symmetric along the diagonal, it goes positive and negative along this. So that is kind of indicative of excitation-induced defacing. If you're interested, I will be able to speak about this further. Let me know. There's a beautiful physics in there. It also evolves with time. There is a lot of detail there, but we'll not talk about that. Another one thing that I want to show, because we had some discussion about Fano line shapes. So here, this is an example done on nanocrystals. So where there is an exciton, which is a discrete state overlapping with a continuum of defect states. And you will see along the diagonal, you'll see some kind of asymmetry in the line shape. And this asymmetry is because of Fano-like interference between the exciton and a continuum. Now, I'm blabbering a lot of words, but that's some kind of intricate process that happens in condensed phase. especially in the presence of a bath, energetically resonant with your thing. So phonon bath and stuff like that are energetically non-resonant, but you could have a bath which is energetically resonant. Then you can have system bath scattering will lead to a generation of a Fano-like interference, which has a very definitive line shape, which we were able to write out the analytical expression for that and see that in an experiment. So the point to note is that many body scattering, system bath interactions comes in different forms and shapes, and that can be all captured in the intricate line shapes of your 2D spectrum. So before we close, I want to talk about discrepancies, problems, right? Let's go back to this excitation-induced defacing. Excitation-induced defacing, okay, is basically what? Presence of an exciton, many excitons, is going to deface this exciton. Now, if I go, is a perfect linear curve. When I go towards the zero intercept of this fit, zero intercept is basically when I have no background excitation, right? No background excitation. If I have no background excitation, there is no bath. In the absence of the bath, what should be the only defacing process? In the absence of the bath, what should be the only defacing process? It's only the lifetime. Because there's nothing scattering. Remember, we have done that considering H naught without our bath. And the only way the defacing can happen is when there is no more excited state, right? It's only determined by the lifetime, okay? So the zero intercept here should correspond to a lifetime, should match with the lifetime of my excited state, right? So if I take my zero intercept that I get from this, of course, the inverse of the line width will be the time, right? So if I find that, it corresponds to about 2 picoseconds. That's experimental observation, 2 picoseconds. Now I can measure the line population lifetime independently using time-resolved photoluminescence, pump probe, whatever, right? Population dynamics. And I know for this particular system, the lifetime should be 100 picoseconds at least. That's a major discrepancy. That's a major discrepancy. To be frank, I don't know why is that the case. But I could possibly know what the problem is. The problem is, I'm coming with whatever you might think, very intense laser pulse. Once I'm coming with very intense laser pulse, I'm assuming that only thing contributing to my response is a third order nonlinearity, right? But there is no reason for the higher order nonlinearities to not exist. They will also exist. They can also be what we call as cascaded nonlinearity. Now, ideally, I would want to be able to go towards that zero density and directly measure the line with that zero density, right? So this is really a problem at the frontier research of nonlinear spectroscopy, because whatever I'm observing, I'm not able to remove possible ambiguity, discrepancy, artifact coming because of high excitation density used in the experiment. And we are figuring out how to go to lower fluences to be able to remove it, possible discrepancy. And that is something that we still ongoing. And one of the possible avenues that we are exploring is to use single photon or entangled photon sources to replace classical light. Now, then we have to rewrite the whole thing that we studied in the last 1 week. The answer is yes, because now we are going to single photon picture. Hopefully, in Tuesday, I will give you some preview on what this is. Remember, what I'm going to talk next is not something that can be available on textbooks or anything. I mean, I'll give some part of just overview of quantum optics relevant here, but some of the claims that I'm going to make may be not true because we are still trying to find answers. So our goal is to be able to go to low enough excitation density to be able to measure at densities where we are absolutely sure there are no higher order correlations playing a role. Okay. Let's stop at this point for today. Okay. Tomorrow's class, which is going to be in the morning, we are going to use QDPi. QDPi to simulate nonlinear line shapes, what we have seen so far, but taking in Hamiltonian, not analytical functions. I can also give you codes. So I have written codes for analytical functions. I'll send it to you. and I can give you that. We can play around with that. But we are taking a Hamiltonian and letting Q-tip calculate the nonlinear response function for us. Okay, let's try to learn QDPi in the next class. And on Monday, the lectures are going to be more on experimental techniques, how to generate short pulses, OPAs, how we do the experiments, so on and so forth. On Tuesday, a bit of quantum optics, and that will be there. Okay. Thank you.